Actually, this work itself is joint work with Dr. Panda's group. Right? So Harry, Saurav, Jonathan, Raghu at one time were all involved with this. Right? So this is on MPI Startup. This seems to have been a discussion point at every mug since the first mug. Right? And just to get the point of that, I can reference myself to some crazy statement in the first one to say, like, why can't we start a gazillion processes in less than a second? And by the way, let's have that done in 3 months, right? Why is that so difficult? The next year we had Elon Musk. He said, I would like an insane mode on MPI run. You may not have noticed that he was in the back corner with me. And then we had someone else. I don't want to break the identity here, so I'll just say the name R.O.K. Oldshay. He said that we need jobs start up mighty fast. And I'm pretty sure that's a direct quote because he's from Texas. So what am I talking about? Well, MVAPICH has the OSU benchmarks, right? And one of those is OSU Init, and this just basically starts out, calls it MPI'lypics, Finalize, and measures the cost of Init. So I recently run that on our new computer, Jade, which is a large-scale interconnect with Intel. We've got about 74,000 processors. That actually goes up to almost, I think, 85,000. Had a couple thousand nodes free, and so I ran this benchmark and I timed it to master run for Intel, MPI, OpenMPI, and MVAPICH. Right here are the timings that you get for that. So it takes about 6 minutes to start up Intel MPI, about 3.5 for OpenMPI, and just about 2 for MVAPICH. Right, so that's pretty good. If we look at the 2016 MPI'lypics for startup, we've got Intel MPI coming in there with the bronze. That's good because there's only 3. OpenMPI got the silver, and gold goes. So the MVAPICH guys have done a lot of really good work. The MVAPICH guys have done a lot of really good work to speed up MPI startup. But when you think about it, 2 minutes really is still a long time. Right? Michael Phelps holds the record in a 200-meter butterfly, and to do that, it only takes him about 1:51. So if he were to swim just a little bit faster, he could do 4 trips down an Olympic-sized pool and still beat MVAPICH in starting up, right? So Michael is happy, and BK's team not as much. Right? So I think we can do better, and that's what this is about. So the first thing I did is, well, not everything is necessarily an MPI so let's also extend this benchmark and call Finalize, right? We'll measure both the Init and Finalize. We'll call that one OSU Init Fin, and I thought, well, while we're at it, why don't we also add in a barrier just to do a little bit of communication, so we'll call this one OSU Init Barfing, and it's probably not the best name. It didn't occur to me until I had to actually read it out loud. But anyway, we run that benchmark, and now we've got a breakout of the cost of MPI'lypics, barrier, Finalize, and then other, which is if you subtract the difference between time and all the rest of the cost. Right? And what you'll quickly note from this is that MPI'lypics really is where all the time is being spent in all 3 of these. Right? And so why is startup difficult? Well, there's 5 tasks you have to do. So from the minute you push MPI run, you've got to broadcast that command out to the compute nodes. You've got to actually start the processes on all the compute nodes you have. You have to read your files in from the file system so you have your application and your libraries. Right? The processes have to sort of discover this global environment. I'll let Mark finish. So the processes have to discover the global environment. So it's like the number of nodes you have, and maybe like how many processes you are on each node and that kind of thing. Each process then opens up a network address, right? And then you have to do some sort of global exchange of those. And then finally, you start connecting all the processes, right? And those 5 different tasks are implemented over the 3 different system objects here. So the operating system, the file system, the job launcher, and the API library, some combination of those. Right, so there's a lot to deal with. So we wanted to look at MPI'lypics and MVAPICH too. And so we stuck in a bunch of timers through the MPI'lypics code. And broke it down. And so this is sort of showing you a profile tree of the Init, and this is on, like I said, our Intel machine, so it's using PSM2. And basically you can see that the costs are sort of scattered all around here, right? So there's a proc sync 1, that's actually something artificial I added in, which is a barrier And the reason I added that in was to detect any kind of process skew in the startup, right? So if rank 0 starts right away, but then the last rank is slow to start, you'll see that show up in this barrier. And then there's various other functions that I won't get into just yet. But we'll start at the top. So we'll look at that process sync 1. That's consuming about 28 seconds of the 2 minutes, right? And so what we noticed is that the very first run in an allocation was always slow. It was always 28 seconds, right? But if you just immediately hit srun right after that and ran again, then the next run might be 8.5 seconds or 3 seconds, somewhere along there, right? So the subsequent runs were much faster than the first run, right? The other thing we noticed was that if we wait long enough in that allocation, even the subsequent runs are slow, right? And then finally, we had a way that we could flush the page cache in the nodes between runs. And by doing that, we were able to verify that every single run was slow, right? So there's clearly some caching going on the compute nodes. And if you've dealt with this problem before, you immediately suspect the file system, right? And so what we did is we built a tool that would go through every executable and library that an executable depends on. It strips out the RPATH, puts them all into a directory, and we copy all those to local storage on all the compute nodes, and then start the run from that local storage. And when you do that, that first synchronization point drops way down, right? And it was consistent. So that sort of verifies that basically it was the cost of reading that executable in the libraries from the file system that was showing up there. So that needs to be dealt with somehow. There are a couple of ways people have been looking at doing that. One of the ways at Livermore is a tool called Spindle. So Spindle runs within your application and intercepts all the hooks to LD or the loader, and then it will fetch files from the file system and then broadcast them out in a scalable tree, right? So that's one mechanism, but it's much slower than I'd like it to be to help with MPI startup. So improvements need to be done there. But ultimately, something like this has to be built into your MPI run or your srun in order to assist with this. Or you need the resource manager to pre-stage those files on your compute nodes before you start running. Okay, so that's the first cost. Now I wanted to look at these other costs, and really quickly, you basically need an overview of something that's called PMI2 before we get any deeper here. Right, so what's PMI2? PMI2 is a program interface that MPI uses basically to bootstrap itself. Right, so there's one call that it makes that will get the number of ranks in your job and the rank of the calling process. It also provides a key value store so that the processes can insert keys and exchange addresses in that way. It's often implemented in your job launcher like SLURM. And I'll just walk you through some example code, right? So at the very top, you just call initialize, that gets you your rank and your size. You have to do this other call so you can call get later. Then you end up encoding your address, your network address, into a key value pair. Usually the key is your rank, right? And you put that in your key value store. You do this fence call to do this global exchange of all the key values. And then finally, for example, if you wanted to read the network address of every other process, you have to make a get call, one for each node in the job or process in the job. So how's that implemented in SLURM? Well, SLURM, when it starts your job, it creates a tree, right? And it's a tree of SLURMDs or stepDs, representing that with these blue circles. Each of those will represent or launch the processes on that node, right? And so when those processes issue a put, the PMI library caches that locally until the processes call fence, and then each process pushes its set of key values to its local stepD, right? When the local stepD has received a fence from all the processes plus all of the children's stepDs, it forwards that set up the tree. It finally gets up to srun, which has the whole set of key values, and then it broadcasts everything back down, right? So it's basically implementing a giant Allgather. And the problem is, if you use this in your code, this is not scalable. So if you assume, like, for example, we have P processes in our job on n nodes, there's little P processes per node, then you have a loop like this where you're looping over to get the value for every process. That scales as little p times big P, and it's a lot of PP. So in this system, P, with P equals 36, the large P 73,000. Oh yeah, this helps. Yep. Yeah, so in this system, you end up issuing something like 2.5 million gets per stepD, right? That's just not going to scale very well. either if you increase the number of processes on the node or if you increase the number of processes in the job. Right? And if you look back at the MVAPICH code, this is again the PSM channel, and where the cost is going. All of these guys are doing PMI exchanges, right? So your populate VCs function. Here you're broadcasting some UUID that PSM needs, and then here's an Allgather of all the network addresses in order to initialize PSM. Right, so we need to fix this. Basically, MPI needs collectives to bootstrap itself, but you can't use collectives if you don't have the connections already bootstrapped, right? So it's a catch-22 problem. And so the solution to that is that we created a library called spawnnet, and we use this to start up our jobs. Basically, this thing is like a little MPI thing, a little MPI job that runs just through MPI Init, right? The network connections it uses are low latency, so it's either TCP sockets with no delay turned on or IBUD. We create these groups, but the groups are represented as these binomial graphs, which scale really well. Each process only actually connects to 2 times log p number of other processes. Right? We have the ability to split these groups into subgroups, so that, for example, we can split the group of world processes into a group of the processes just on your node, and a group that represent all the nodes you have. And then we implement a bunch of collectives over this. So we have barrier, broadcast, reduce, Allgather, and a shift. But the important thing is that we're able to start up this structure just based on a ring, right? So from a ring, if you just give me this, or at least the addresses needed to make this connection, you can get from here to there in log p time. Right? So there's an efficient way to do that. And then how do you get the ring? Well, there we just use PMI. Right? So again, we encode our address at the top with a put. We do the fence for the global exchange, and then we look up the left and the right partners, and now we have a ring. From there, we can get to this other structure. Right? That reduces that complexity I was talking about earlier from p times p to p plus p. So it's a huge difference already. If you look at what that does to the startup cost, there's some overhead in actually creating these the spawnnet groups, right? And so here I'm actually breaking out a world group, a node group, and a leader group. The leader group goes across the nodes, right? But to set all that up takes maybe about 5 seconds. But then it reduces the time for all the other exchanges. So we've saved almost 20 seconds in the populate VCs, saved another 6 in the Shmen call thing, and another 28 in gathering the endpoints, right? And then there's a little bit of teardown cost. But the net savings is about 50 seconds in the startup. So that's good. That helps a lot. But man, it's too bad we had to pay that 5 seconds just to get the thing going. It would be nice if we could fix that too, right? So that's the next thing we looked at. And the solution here is that we use something called PMIX ring, which is a new API that we added in. Actually, sort of had a paper in Euro MPI about this, and it's been added to SLURM. And what that allowed us to do is we replaced all of the code on the left with the code on the right. Right? So the coding is much simpler, but the other difference is that PMIX ring operates more like a scan operation rather than an Allgather operation over your SLURM tree. And so it scales much better. We again reduce this complexity from p plus p to just p plus log n, where n is the number of nodes. Right? So another big savings here. This has been available in SLURM since 1508. Right? So if we just turn that on and use it, now we save basically another 5 seconds from the startup. So it's another savings. Now our initialization time has dropped all the way down to about 14 seconds. All right, so what's left? If you look at this, it basically boils down to this Allgather and the connect, right? So what's happening in this PSM EP connect is that it's basically doing an all connection phase within PSM2. And that's now taking 11.4 out of the 13.8 seconds that are left, right? So the vast majority of the time. So we need something fixed there. Unfortunately, I can't do that. There's 2 ways that you can eliminate this. One is that we need Intel to re-implement PSM2 endpoint connect so that it does this all more efficiently, right? There's ways to do that using like Brooks algorithm or something. The second way to do that is to switch over to a connection manager type approach, which MVAPICH already uses in the Gen 2 channel, right, but not in the PSM channel. And so this is something the MVAPICH team could take care of. So basically it boils down to Intel versus MVAPICH to fix this one. So I think that to resolve this, we should have Ravi and Harry arm wrestle tonight over dinner, and whoever wins, the other person has to implement the solution. So.
I'll push you over to Intel side as well. Because I like currently PSM, I think we discussed this yesterday, PSM does not have the necessary support to do a good connection manager.
Yeah, I heard you say that, but then there's no way I can get an arm wrestle match. So. But okay, so how have we done in this? If we take a look at what we've got, here's on the left, this is what we started with, the baseline. If we stage in the executable in the libraries, the time drops down, if you look at this top line, 96 seconds down to 68. If we replace PMI2 with spawnnet, we save another 50 seconds. Add in PMIX ring, we save another 5. And I think that with connection manager, we could actually drop this down to less than 3. Right? I'm estimating that based on what I know it costs to set up the Gen 2 and what I think it should be able to cost on PSM. And so that now our total MPI knit time went from 110 seconds all the way down to something under 10 on this system. Right? And so with that, I'll go ahead and end here. So now Michael Phelps is sad and Dr. Panda's team is happy. So we've restored peace in the MVAPICH universe.